What we're going to do now is we're going to continue and hopefully, knock on wood, wrap up the bulk of the remainder of the overview of the Java programming language. If there's anything left over at the end, it'll probably be things about collections, and we'll cover that at some other point. So what I'd like to do, and to focus the bulk of this discussion, is to emphasize inheritance and dynamic binding. Those are the key features we're going to talk about. And we're going to show lots and lots of examples. We'll show even more examples than we did before, and you'll also find that there are examples you can download and play with in the GitHub repository that I put out there under the examples directory, or the EX directory. So before we can start talking about inheritance and dynamic binding, it really helps to have a better view of the context in which these features are used. And the most common way that they're used in Java, as in many other languages, though not all, is by something called frameworks and callbacks. And these are very important, and you'll see in a second how they apply all throughout Java, and they also apply heavily throughout Android. So what is a framework? Well, a framework is basically an integrated set of components, where components could be classes or objects or functions or various things, that collaborate to provide a reusable architecture for a family of related applications. It's kind of a mouthful, but the basic idea is there are things that work together, they are coordinated, they're integrated, and they provide you with a reusable architecture that can be customized or tailored for particular application needs. So you're not building an application, you're building a framework for a family of applications. And I'll show you lots and lots of examples, and you'll recognize a lot of these examples as we go through this stuff. There's an article I wrote many years ago that gives more details about this. Oftentimes, frameworks get used with event-driven programming. Not always. There's lots of examples of frameworks that are not used with event-driven programming. But the place where you're most likely to encounter it when you first start writing user interface-driven applications is with event-driven programming. Now, let's talk a little bit about this. So basically, event-driven programming, which you can read about at the Wikipedia link, is a way of being able to provide an inversion of control in your software so that you provide handlers that get called back when events occur. And you are not responsible for detecting the events or demultiplexing or dispatching the events to the event handlers. All you are worried about is the application business logic or application logic that does the real work. So here's kind of how it works. An application registers some event handlers, which are essentially known as callbacks, for specific types of events that can occur within the framework. So in the context of an user interface environment, there's a lot of things you would register for, like you might register for different kinds of gestures, like clicking or swiping and so on. Those would be gestures you would register for. There's also a bunch of so-called life cycle actions we'll talk about later, things like your application is started, your application is stopping, your application is pausing, your application is resuming, and so on. And these are all events that you might care about in order to write your application properly. When we start talking about Android, you'll see lots of examples of that. So you register these callbacks for specific types of events that can occur, and then the framework goes ahead and waits for those events. So it might wait for clicks on a GUI widget or a network message should show up on a network connection or whatever. And when those things show up, the framework automatically calls back to your application code, to your event handler that you registered previously, indicating your interest in dealing with this kind of an event. And that's commonly called inversion of control. We'll talk more about that in a second. And the application then goes ahead and does its thing, whatever its thing is. Maybe its thing is to throw up a dialog box to interact with the user. Maybe its thing is to render an image. Maybe its thing is to upload or download a file or whatever, right? The application can control what happens next. And when the application logic is done, which is typically done very quickly, by the way, code returns, the control flow returns back to the framework, which waits for the next event to come in. And this whole thing goes on over and over and over again. So that's typically the way that event-driven applications are structured. What would be the opposite of an event-driven application? Does anybody want to hazard a guess about that? So the opposite of event-driven is self-directed. I'm going to take a guess that many of the application programs or assignments you've programmed up to this point, at least in maybe 101 and 2.1, were largely self-directed. You wrote a main program probably, and you declared some objects, and you invoked some methods, and when everything was done, you shut down. That's a self-directed application. The application decides what it's going to do and when it's going to do it. Frameworks are different. And one of the main characteristics of a framework, of the three characteristics, is so-called inversion of control. And I should have put a link up here to something called the Hollywood principle. I'll explain that more in a second. So inversion of control basically says you don't decide when activities occur, when actions occur. The framework decides on your behalf. So it inverts control. The framework owns the event loop the bulk of the time, and it lets you periodically borrow it when something interesting happens. Now, this is sometimes humorously referred to as the Hollywood principle, which says, don't call us, we'll call you, right? So if you're, George Lucas or Steven Spielberg or any of those discredited executives in Sony Picture Entertainment, right? You're a Moogle, and you don't call people, or people don't call you, you call them. So that's kind of what a framework is. A framework's like a Moogle, and it's going to call you back when it feels like it's your turn to do something. You ever watched the movie The Godfather? There's a great scene in The Godfather where the guy asks the Godfather for some justice for his daughter on the Godfather's daughter's wedding day, and he says, someday, and that day may never come, I will call upon you to do me a favor. So he's going to call him back, right? So that's inversion of control. The other thing that frameworks do is they have integrated domain-specific structure and functionality. And what that really means is that the framework is customized for some application domain. It's not intended to be entirely domain independent. Can anybody think of an example of a pretty domain independent abstraction that we deal with, we've talked about in Java? Yeah. An array, great, good. Tristan? Vector, string, right? Vector, array, string, these are all things you could use pretty much anywhere. They're really not domain specific except the domain of writing programs, right? That's a very broad domain. But there's also domains like the domain of graphics or animation, right? Feature picture animation. There's the domain of social media. There's the domain of financial services. There's the domain of graphical user interfaces, right? There's the domain of real-time avionics control systems, et cetera, et cetera. And frameworks focus on those kinds of things. And you'll see some examples. We're going to focus on domains like graphical user interfaces or concurrency frameworks and so on. And these frameworks provide domain-specific groups of classes that have interactions between abstract and concrete classes. We already talked a little bit about abstract classes. You've seen a couple of examples. You'll see more in a second. Tristan?
So those would be like the, I think it was last Wednesday when we showed us example packages like net and applet.
Oh yeah, well, so those were examples of packages. Applet. So yeah, an applet's a pretty good example of a domain-specific thing. It works very well when you're trying to download behavior into your browser, right? But oh, an applet is absolutely a framework. Yeah, because there's a method, I forget what it's called, but it's like apply or something like that. And that's what you fill in to do the work when the applet's downloaded. Yeah?
So the Android development kit is a framework?
The Android development kit, so the question is the Android development kit a framework? Well, we'll talk soon enough about the Android development framework in tremendous detail. And you'll see that the Android development framework, well, the Android development platform has many, many layers. And one of the layers in the Android development platform is called application framework, which really should be application frameworks because there's actually a whole pile of them. But there's also frameworks in many other layers as well. There's also lots of other stuff in Android that are not frameworks, but frameworks play a very important role. And certainly the user interface part of Android is heavily framework driven. But the key point is that they mediate interactions and they handle domain specificity. The third and final thing for now we'll talk about with respect to frameworks are that they provide semi-complete applications where you come along and plug in the application code. And I'll show you a bunch of simple examples of this in just a second. But the main concept here is that you don't have to write a gigantic amount of the software. You simply have to find a way to customize the stuff that's already there. And so that gives you a tremendous boost in terms of productivity, in terms of reusing stuff that somebody's already done, in terms of applying the don't repeat yourself principle at a grand scale, and so on and so forth. And these are typically called hook methods. We'll talk more about hook methods. Hook methods are simply virtual methods that can be overridden by subclasses, and we'll talk about that. All right, so Android and Java provide lots and lots and lots and lots and lots of frameworks. Some of them are very big and very significant. Others are very small and very tiny, but they're all frameworks in terms of what we just talked about. Let's take a look at Android first. So Android has something called the activity framework, and this controls the behavior of the main thread of control in an Android application. And one of the key things that the activity framework does is it manages the life cycle of various kinds of actions that can be called back at certain times by the framework when interesting things occur. And I'm not going to go into this in great detail now because we're going to go into it in great detail later. But in a nutshell, when you create an application in Android, when an application is launched, there's an entry point called an activity. And the activity has about a half dozen or so lifecycle methods. And these lifecycle methods do things like get called back when the activity is first launched. So it's kind of like a virtual constructor that initializes the activity and initializes global state and inflates user interface elements and views and so on. And then as the activity runs, different things can occur. One thing that can occur is you can hit the back button on the phone, and that calls the activity to be destroyed. And so the onDestroy method gets called. So onCreate is creation, onDestroy is destruction. For those of you who are Hindu, what Shiva is the destroyer, and who's the creator? Brahma. Okay, so onCreate, onDestroy, right? Things come into existence, they go away. OnStart, OnStop are also used to control the life cycle. OnPause, OnResume, and so on. We'll talk about all these things in more detail, but the point is that there's these life cycle events occurring external to your application, and the framework calls you back to figure out what to do about that. And the third programming assignment will give you a chance to start playing around with some of this stuff. So here's another example of what the framework does. So those lifecycle methods are one thing the framework does. The framework also is used to listen for button clicks. So here's a simple example where we go ahead and find a button. We look up the button by its ID, and we get the button back. And then we go ahead and we set up a click listener, which is basically anonymous inner class in Java. And it's got an onClick method. And when a user clicks the button, right, when they press the touch screen or do whatever they do to get it depressed with a pen or their finger or whatnot, that ends up causing the framework to dispatch the onClick hook method of the click listener object. And so we'll see how that works, and you'll get a chance to implement a bunch of those kinds of things. And it's really cool and really easy to do in Android. You'll be amazed at how powerful it is and how little code you have to write when we go through that. All right, so those are some examples of Android things, and we'll get to those in a couple weeks. Some other stuff, which we'll hopefully get to later in the class, is Java threading. So does anybody know what a thread is? A thread is a process. So sort of, but what's a process? How about unit of computation? Tristan, do you want to take a shot?
I was going to say, I guess, process.
OK. So we'll learn more about this later. A process, as we typically mean it in the context of this course, is a unit of protection and resource allocation. And within a process, there can be multiple threads. And a thread is a unit of computation. And you can have multiple threads within a process, and those threads can execute so-called concurrently on multiple processing cores. Or they can be time sliced on a single core. So a thread is a unit of computation that executes a stream of instructions. The key point of this is that there's something called a thread. And in Java, you can come along and you can say, make me a new thread. So we make me a new thread. And then you can say, start that thread. And when you start a thread, a run hook method gets called back on the thread. You can define what that run method does. So that's an example of a framework. All the other stuff that's going on under the hood to get that thread started to run on a separate processor core is all handled by the threading framework, and you just have to fill in the hook method to define what it's going to do when it runs. Yes?
How come some applications have multiple processes? Like Chrome has like 10 processes, Chrome.exe.
How come some applications have multiple processes? Great question. So that's a little outside the scope of what we're talking about, but I would be happy to answer it. So a process is a unit of protection. And oftentimes in complex systems, we want to make them resilient. So if one piece of computation going on in one part of the system goes berserk, the whole rest of the system doesn't come crashing down, right? If you recall the ill-fated Titanic, right? Famous ocean liner from 100 years ago or so. What was the thing that caused it to sink? It wasn't cold. That's what caused everybody to die. But the ship didn't sink from the cold. An iceberg, right. And what was the reason why the ship sank when it struck an iceberg? Yes, ma'am.
Compartments that were supposed to keep it afloat, didn't go up all the way, I guess?
Perfect. Exactly. Yes. You're absolutely right. So what happened was there was not proper isolation between the different segments of the ship. And so when they got water in one part, it caused the water to go over the compartment top. So the real point there is not how the Titanic sank, but isolation is important for robustness, right? And there's lots and lots and lots of examples in real life where you want to compartmentalize things. If you work for the CIA, then you have a need to know, and you don't tell everybody the secret. You only tell the people who need to know. It's called compartmentalization, right? So the same thing is true with robust systems. You want them to be robust. And so if one thing goes awry, you want someone else not to be affected, and we'll talk later about how it is not affected. And more importantly, you want somebody else to keep track of that thing and say, this guy's crashed. Let me start up another one, right? So the reason why you have multiple processes in those systems is so that they can be isolated from each other. And you want to isolate it from each other for robustness and reliability purposes. Yes?
Can you give us an example
Of a thread? Sure. The main, when you run your program, when you write a Java program, like the Java program you're writing for your first assignment, and you run it, there's a method called main. And that is running in the main thread of control. If you want more than one thread, you have to spawn the thread, and there's a variety of ways to do that. We'll cover those things later. But the main function in your Java program is running in a thread. Everything runs in a thread. Yeah?
So we talk sometimes about the control flow in terms of is a thread like a single instance of control? Is it a single line of control flow?
The best way to think about a thread, and this is a terrible anthropomorphization, is like a person, right? And you can have one person doing a set of things, and if you want to have someone else doing things in parallel with them, you have another person and they're running in parallel, right? Yeah?
How are threads not compartmentalized or protected from each other already?
Good question. So the question is, how are threads not compartmentalized? So threads in a language like C and C++ have the unfortunate consequence of being able to scribble over each other's stack and memory in various randomly bad ways. In Java, that's much harder to do. But threads within a process can share globally visible data, and like static data or objects that are given, passed and made global to them. So they are not prevented from accessing each other's memory. In contrast, things that are in separate processes are unable to access each other's memory because they're protected by something called a memory management unit. And we will talk a lot more about that. Was there another question? OK. So threads provide a hook. We'll talk more about threads later in the class. Actually, the CS282 class, which is something you may want to take. If you like this class and you like this style, you'll love CS282, which you can take next year. We'll go into this in great detail. We'll probably also cover it here as well. There's also something else in Java called the executor service, which you can learn about here. And this allows you to have a pool of threads, and so you can actually run things in the pool of threads. So what a good example of a pool of threads from a human known use example would be a call center where a group of people handle incoming calls to place orders or get technical support or whatever, right? You have a pool and calls come in and they're routed to available to operators, right? Operators are standing by. Those are two simple examples of threads in Java. There are lots and lots of frameworks in Java. There are lots and lots more. Some of what you'll implement in this class will implement frameworks. Everything in Android is going to be using frameworks. Most stuff in Java uses frameworks as well. So all this stuff was leading up to the following, which is inheritance and dynamic binding are at the heart of frameworks. And so that's what we're going to talk about next. So here's some examples, abstract classes and interfaces. Here we'll see an example of a thread, for those of you who want to see an example of a thread. This is an interface called Runnable that has a method called run. Notice that this is your classic Java interface. There's no default method. There's the implementation. There's just an interface with a single method called run. This is called a functional interface. We'll talk more about that later. Here is an example where we go ahead and we make a new instance of Runnable, and we define its run method to print hello world. And then we start this thread, and what will happen here is, imagine for sake of argument, that this piece of code appears somewhere in the main function of your program. So the main function of your program is running along kind of like this. It's doing some work. And it goes ahead and it makes a new thread, and it starts it. And now your new thread's run method is going to run. And in this particular case, it's going to print hello world. But while it's running and doing its thing, which, by the way, could be something more interesting than printing hello world, this other thread of control is running concurrently. So now you've got sort of two things going. Anybody here ever see the classic movie, the classic Disney animated movie Fantasia? So does anybody remember The Sorcerer's Apprentice? So what did The Sorcerer's Apprentice do? He spawned new threads / brooms, right? Because he was lazy and he wanted them to do his work for him. So after a while, he kind of got over, a little carried away, and there were lots and lots and lots of brooms. And we'll talk about that later in the course because it does figure into the discussion. But for the purpose of this discussion, we can have multiple threads. They're each running independently with each other, and that leads to all kinds of good and bad things. This is an example of an anonymous instance of an inner class. This is very, very common idiom you'll see a lot in Java and Android. Here's an even wackier, even cooler example. This is an anonymous instance of a lambda expression. So here we're doing exactly the same thing we're doing there, except now we're using a lambda. So we're saying, make me a new thread that prints out hello world and start it. So this is sort of for people who are suffering from serious carpal tunnel syndrome because there's very little typing involved. Yeah?
Are those missing parentheses, or is that the syntax?
That is the syntax. That's the syntax for lambdas. This is saying, it boggles your mind when you first see it. What it's doing is it's saying, give me something that takes no parameters, like the run method, and make this the implementation of it. So don't worry about it. We'll cover it later. I'm not going to quiz you on the syntax of lambdas for next class. But it's super cool and very parsimonious, right? Very short. All right. So that's a quick rundown. Let's talk about inheritance now. So in Java, as we talked about based on the quiz, a class can derive or extend or inherit, whatever you want to use. The words all mean more or less the same thing, from another class. One class can derive from another class. And so in this particular case, this is an example of inheritance, right? You get some properties of your parents, of your ancestors. And you use the extends keyword. So in this particular case, we say that vector is a subclass that derives or extends or inherits from the superclass. And keep in mind, in Java, there's one and only one superclass for every class. Methods that are inherited from the superclass can be used for three typical purposes. Yes, sir?
Is there only one subclass per superclass?
There's not one subclass per superclass. Boy, that would be very restrictive. But any superclass can only have one. Any subclass can only have one superclass. So you can have gazillions, and you'll see in a second. I'll show you examples of gazillions of subclasses. Okay. So one reason why you extend the class is to inherit the data and methods. So you can then go ahead and let the user of you use what you inherited, right? So here's an example where class stack extends vector, and it inherits the isEmpty method from vector. So you can say, stack integer s equal new stack. If s not empty, negation of that, pop. So pop comes from stack, but isEmpty comes from vector. So one reason is this is a don't repeat yourself thing, right? You can extend something and reuse what it's already got. That's one reason. Another, and this is what's called implementation inheritance, which is actually somewhat frowned upon, but for some God knows why reason they do it all over the place in Java. Here's another example. You can add new subclass methods that are implemented in terms of stuff that you inherit from the superclass. So here's a case where the push method of stack is implemented by adding an element to the end of the vector. Yeah? Implementation inheritance basically says that you're inheriting the implementation, not overriding it. So we had an isEmpty method that occurred in vector. We have inherited the implementation of isEmpty. We have not overridden isEmpty. We've just made it part of the interface of stack.
Why is that?
Because it's confusing and it doesn't really play off the strengths of inheritance, which is dynamic binding, which we'll talk about later. Yeah?
Can you override isEmpty?
Yes? The only reason you could not override is empty would be if it was final or static. This is the main reason that you use inheritance, though. The other reasons were not so good reasons. You want to be able to override superclass methods in the subclass. And the way that works is that you have the subclass define methods with exactly the same signatures as the superclass. And that process is called overriding. And so here's an example, which we'll look at later. We have an abstract map, which has an entry set method. It's abstract. And then hash map, which is a subclass of abstract map, which is a superclass, extends and overrides entry set to do something to give you back the set of entries in the hash map. We're going to talk about this more in a second. All classes inherit from java.lang.object, whether you realize it or not, whether you explicitly deal with it or not. And there's a whole pot of methods that they have defined here. We will talk about a lot of these later. Even if you don't explicitly inherit, even if you say, public abstract class process, blah, 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 you will still inherit from this class implicitly. It's always inherited from. So in a sense, using good old UML notation, here is class process, which inherits from class object. That's just a funny UML notation. You should know a little bit of UML notation. Google UML or Unified Modeling Language, distilled or something like that, and you'll get very, very basic stuff. It's simple. These are methods. That's the name of the object. That's inheritance. There's other relationships we'll cover later. Everybody, therefore, object is at the root of all classes. And everything, arrays, whatever, inherit methods from this class. Now, if you recall, we talked about equals versus operator equal equal. Operator equal equal checks to see if two objects have the same address, whereas equals checks to see if they have the same contents. And that's, of course, a different thing. And if you recall the last discussion we had about strings, where when they were assigned the same string literal, then they had the same address. But if the strings had the same value that were computed dynamically, then they wouldn't end up with the same address. And there's a bunch of good reasons for that. The reason why string literals have the same address has to do with the way that compiler optimizes string tables in the so-called constant pool in Java. And it goes ahead and it sticks them in a constant pool so that every time it sees a string literal, it goes ahead and checks to see if that string literal has already been defined and is in the constant pool. And if it hasn't been, it goes ahead and adds it. If it has defined it, it just goes ahead and returns the address of what's already there. So that can be done at compile time in order to optimize. But if it's a runtime lookup, then it doesn't know that. Yeah?
Are you using the collections interface with something like a hash map or an array list? Is that using the dot equals or is it using the compares?
It's going to use equals. OK, so that's inheritance. Inheritance is actually quite simple. There's not a lot to it. The key thing to remember with inheritance is the most important kind of inheritance is inheritance of interface methods or methods that are going to be overridden. That's important. Implementation inheritance, it's sometimes done, but it's kind of crufty and awkward and so on. Overriding methods is the secret sauce of inheritance, and that's because it works with this thing called dynamic binding. We're now going to look at a very specific example, which is kind of fun, and you can look at this online when we get to it. So a subclass can override methods from a superclass. So here's abstract map with entry set and put, and any non-final and non-static method can be overridden. So by default, just a normal Java method is capable of being overridden. The map class hierarchy in the Java collections framework is a good case study for this stuff, so we'll use that. So the entry set method returns a set view of all the mappings contained in the map. And for the abstract map, there's no way to know what that is because we don't have an implementation yet. The put method associates the specific value with a specific key in the map. This is back to the earlier question about can a superclass have more than one subclass? The answer is yes. Here's an example. So abstract map is a superclass. It can have tree map, hash map, concurrent hash map, and there's several other predefined examples of collections, map-based collections in Java. And then, of course, you can define your own if you want to. If you want to go to the trouble of writing your own kind of map, you can go to town and override those methods too. This is an example just showing inheritance, and each of these guys is a subclass of abstract map. And the main issue here is that they implement put and entry set in different ways. Of course, they also implement other methods differently too, but those are the ones we're going to focus on just to keep the example bounded. All right, so here's a fun example. I'm just going to show you it quickly, and I'm going to show you the code. The code is available online. You're welcome to play with it at your heart's content. You're welcome to go in and modify it in your heart's content just to see what it does. So what we're going to have here is we're going to have a main program that uses something called a factory method, which we'll talk about a lot more later. And you're going to pass in the kind of map that you want as a string, and it's going to give you back the appropriate implementation that you requested. So you can say, I want a hash map. It'll give you a hash map. I want a concurrent hash map. It'll give you a concurrent hash map. I want a tree map. It'll give you a tree map, and so on. And once we've got this map, then we can go ahead and make method calls on the map. We can say, put I am Iron Man with various, I guess actually, I don't know, nobody will probably know what this is, but how would you really say I am Iron Man? There you go. That's good. Somebody knows 1972 Black Sabbath. Very good. Give yourself 5 points. So once we've got this, now we can go ahead and we can get the entry set for the maps, and we can walk through them one at a time and print them out. This is an example of a for each loop, which we'll talk about later. All right, so if you go to this link, you will find this code, and here's the code. And I will run it for you just to show you what it does. So you can go over here and say run as. Oh, sorry. Thank you. Just have to exit the slideshow. I always forget to do that, by the way, so thank you for reminding me. All right, so here's the code. And if we go up here, we can go ahead and run. Let's see, let's go and do run configurations. So we do run configurations, and I give it hash map. Maybe a little hard to see that, but if you could squint, you could see it says hash map up there. That's the thing we're going to pass to the main program. And so that goes ahead and runs this, and it prints out basically, well, you'll see what it does. It's telling which method it's calling, and then it goes ahead and prints out the values. Now, if I want to change what I do here, all I have to do is come over here and do run configurations, except this time, let's say we say I want to do a tree map. Whoops. So I apply and run. And now, if you could see that, it says simple tree map as opposed to simple hash map. Here's the actual code for this stuff. Let's see if I am smart enough to make this bigger. All right, so go to Java, Appearance, nope, Colors and Fonts. And we want Java Editor. Well, let's do edit. Let's make this guy even bigger. All right, there we go. That's a little easier to see. So what's going on here is we have a dynamic binding test, and we have a abstract class. Ignore the static. The static was just so I could be lazy and put everything in one file. If I had not wanted to be lazy, I would have put it in separate files. So I have an abstract class called simple abstract map, and I define an abstract method called entry set, and I define a non-abstract method, and I think I will make the font even bigger because it's probably still too hard to see. Yes, this should be readable. All right, there we go. So now you can see that we have a put, which throws an exception, and entry set, which is abstract. Down here, I now have simple hash map, which inherits from simple abstract map. And this guy does something very simple just to make the example work. He prints out the name of the method that's being called, and he also defines an instance of hash map, and he simply forwards the request to the instance of the hash map. That was just so I could make something do something interesting. That doesn't really matter. Here's the put method. This says I'm simple hash map put, so you can see that these guys call that. Here is simple tree map, which makes a tree map, and it prints out what the implementation method's being called, and then it forwards to its implementation. Simple concurrent hash map, same kind of thing. Here's the secret sauce for all this stuff. This is the so-called factory method called makeMap. I pass in a string, which is the type of map I want, which I gave as a command line parameter, as you saw, as an argument to the program. and he goes ahead and checks to see what kind of map I'm requesting using equals, as we just talked about. And he then returns simple hash map or simple tree map or simple concurrent hash map, et cetera, or he throws an exception. And then down here, we have the make map method, which is a factory method that takes the parameter passed in, makes the appropriate type of map. And the cool thing about this is all this code is completely generic. It doesn't matter whether it's a hash map or a concurrent map, or concurrent hash map, or a tree map, or whatnot. The code is identical, and I make method calls on it. I iterate through it, and so on. And it's the way it's created that gives it the power of selecting which implementation to choose, because it's using the runtime type to make the choice. Yeah?
What's the difference between an abstract method and a final method?
So a final method is basically saying, this guy is the one and only. That's it. No more extensibility possible. It's like constant, or it's read-only, if you will. In contrast, an abstract method is sort of the opposite. The abstract method says, I don't know what I'm going to do, but you're going to have to figure it out for me. You have to fill in the blanks to implement this thing. A non-final, non-abstract method that's not static is just a good old virtual method. And that method can have a default implementation, but you're capable of overriding it in a subclass if you so choose.
So abstract methods can have implementations?
Abstract methods cannot have implementations. Final methods cannot be extended. So abstract methods cannot have implementations and must be extended. Final methods cannot be extended and must have an implementation. A non-final, non-abstract, non-static method can have an implementation and may be extended if you choose to. So we'll cover that more in detail. If that went whizzing by some people, that's OK. We'll cover it again later. Yeah?
So if this was done at compile time, if the binding was done at compile time, it wouldn't work like this?
So good question. So one of the things that's cool about this, as you can see, is I'm selecting which implementation I want when the program runs by passing in a string from the command line, right? So that's called dynamic binding. Conversely, if we define those things as final methods, which would require a massive rewriting of what I have up there, so I won't just make a simple change to show you, then the binding would be done at compile time, and the selection could be done at compile time, and the method lookup could be done and optimized without having to use dynamic dispatching. Danny? Well, let me show you what it looks like. That's actually a good question. So let's go back to the slides, and I'll show you an example of this, if it works. All right. So this is how dynamic binding works. I paid Danny to ask that question, so it would be a segue. So up here at the top, you see the part that says abstract map. So this is what an abstract map looks like. An instance of abstract map has got some fields, the key set field and the values field. Those are some fields that the abstract map has. And then it has something that's a pointer to a vtable. A vtable is a virtual table. And the virtual table is an array of pointers to method code. So you can see for every method, like a method might be entry set or put or set or whatever the methods are in abstract map. Every one of the virtual methods, i.e. non-final, etc., has an entry in this virtual table. And so when you invoke a method, it actually turns into a lookup, which is optimized out the wazoo, by the way, by the compiler and runtime system, that goes ahead and calls the appropriate method at runtime. This is a hash map. A hash map is going to have all the abstract map stuff in it, and then it's also going to fill in some other fields that it also adds. I should put like a ... here, because these are other fields that this stuff gets concatenated here. And this guy has a pointer to a vtable, except his vtable is a different vtable than that guy's vtable, because his implementation of put, for example, is different from this guy's implementation of put. The abstract map's implementation of put throws an exception. The implementation of put that comes with a hash map does a put. It actually stores it in the hash table. So that's got a different implementation. And so at runtime, when you invoke a method, it goes and it looks up at the vtable, and it goes and finds the array of pointers to methods, and it invokes the appropriate method. All that stuff is done under the hood for you behind the scenes. But it's very cool. We can talk about that later if you're interested later in the course, because it's pretty cool to know how it works. But you don't need to know how it works in order to use it effectively. And this is basically what's called dynamic dispatching. And there's a whole bunch of different ways to do it. All right. So any questions about any of that stuff? Yes, sir.
So do all classes use vtables, whether or not they use variables?
All classes have vtables. I guess you could, well, I would say all classes use vtables, but it's possible that for some really special implementations where the compiler could figure out you had a class with only final methods, et cetera, it might be able to optimize them away. But that would be an implementation detail of the virtual machine and compiler. I think it's probably fair to say without too much regret that, yes, everything has a vtable. So everything has the capability for dynamic dispatch, although some classes wouldn't need it if all they had were final or static methods. OK, any other questions? Tristan?
Is an inner class the same thing as a nested class?
An inner class is a nested class. Keep in mind that there's two types of nested classes. There are inner classes and there's static classes. There are two different types. But yes, an inner class is a nested class.